Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is the first of 4 in a second series on centre of mass and moments, and it's about the equilibrium of rigid bodies. What's the difference between a particle and a rigid body? Well, a particle is considered as a mass at a single point, so it has no geometry other than its position. A rigid body does have geometry, and the position at which the forces act upon it make a big difference to whether it's in equilibrium or not. Think, for example, of how it matters where you sit on a seesaw. If a body is to be in a static equilibrium, there are two principles. The first is that the resultant force considered as a vector sum must be equal to 0, and the second is that the total moments of all the forces about any point must also equal 0. Applying those two principles with a judicious eye to the slickest solution is what this kind of mechanics is all about. In general, we can do three things. The default option is to resolve in two directions and take moments about one point. But there may be good reason for resolving in one direction only and taking moments about 2 points, or taking moments about 3 points, so long as they're not on the same line. Let's begin with the problem about a uniform rod. It's hinged at a wall at the point A, freely hinged, so there's no torque there. The rod would simply flop below A if the cable CB were broken. The rod's held in equilibrium in a horizontal position by a cable at BC, and we assume it doesn't sag. In other words, it's a light cable, so it has its own weight doesn't contribute. We're asked to find the tension in the cable. Now, this sort of problem involves always a good force diagram to begin with, so here we go. There'll be a force from the hinge at A that's supporting the rod, but we don't know what direction it's in. That's why I've put it with a zigzag line. There'll be the tension in the cable, which will be along the line of the cable, and hence the 40 degrees is transferable from the first diagram. The weight for the beam or the rod can be considered to act at its midpoint. That's what the principles of centre of mass are all about. So we put the 5G at the geometrical centre and the weight force going vertically downwards. Now, from all that, we're trying to find the tension in the cable. Now, the clever thing to do here is to take moments about A. Now, why is that? Because the force that acts at A, whose direction I don't know, can be completely eliminated that way. If you do anything else, you'll have to bring A into the problem. So if we take moments about A will have no moment. The force at A will have no moment, whatever its direction, so we can simply balance the T and the 5G in moments terms. So anti-clockwise, we'll have T. Now we've got to resolve it. It's going to be sine 40 upwards. There'll be a component T sine 40 up that line, and T cos 40 along BA. But the T cos 40 passes through A, so has no moment. So we just need the T sine 40 times 3, and that will balance the 5G times 1.5. So from that we've got an equation for T, which is 5G times 1.5 over 3. I make that to be 2.5G over sine 40. So we reach for the calculator and put the numbers in. That gives us the answer. 2.5G over sine 40 with G as 9.8, and we get 38.11, etc. So that's the tension in the cable, and we can give the answer in context to an appropriate degree of accuracy. So what comes next? We're now to find the reaction force at the hinge. Well, this time I can't compromise on the way I show it. So there I've given it two components, x and y, otherwise the diagram's unchanged from the previous bit. We do know what t is. Now, the crafty thing to do here is to realize that if you take moments about the other end, b, you eliminate t. So we get something for nothing straight away. So if we take moments about B, we eliminate T, but we also eliminate X, because the force X along the line of the rod passes through the point B where we're taking moments. So there won't be any moment from that either. So we'll simply be balancing the 5G times 1.5, that's the weight about B, that's counterclockwise, and that must balance the Y times 3, that's the moment of the Y force about B. So that gives us an equation for Y, which I reckon is 5G over 2. 5G, yes, 1.5 over 3 is a half, so it's 5G over 2. And with G as 9.8, we can work that out. Let's now also resolve horizontally. Now if we resolve horizontally, that is also rather sly because it eliminates both Y and 5G. They have no horizontal components. So balancing force to the right against force to the left, we need the component that we were able to ignore before, T cos 40 of the T force along the beam. Now from the answer on the previous part we can put numbers into that and get the answer for X and Y. So let's do that. So I've fed in for T the answer from the previous part. It was 38.11, that will still be in the calculator, and I've worked out the 2.5 G as well. So we end up with two numbers for those components. Now if we're to find the force and its direction, we need to draw ourselves a Pythagoras type triangle, that is to say a right angled triangle. Now that right angled triangle has the vertical component y, which is 24.5, and it has the horizontal component, which is 29.19, etc. Again, I'll quote that from the calculator if and when I use it, and we'll give this an angle theta. Now the force that we're interested in is along that line, and we'll call it R. So using Pythagoras, we can say that R squared is the square root of the 24.5 squared plus the 29.19, etc., taken from the calculator, squared, and that will give us an answer. For the angle theta, that will be the angle whose tangent is the 24.5 divided by the 29.19, etc. Notice I always put the dots in if I'm quoting from the calculator. So that will be a matter of two numbers. So there's the figures. 38.11 is the answer that comes out for R, and the angle is actually the 40 degrees again. If you think about the force diagram, it's actually bound to be symmetrical, though that's not glaringly obvious. So we get those two answers for those measurements for that force. So there's the answer in context to an appropriate degree of accuracy. Let's now move on to a final problem. Here we have the centre of mass of a non-uniform rod AB. Mass 5 kilograms and length 3 meters. It's 2 meters from A, so the centre of mass is about there. That's where we can say its weight is acting. It's freely hinged to a vertical wall at A, and it's held in equilibrium by a force T newtons, which is at right angles to AB. So, as usual, we can't do anything with that until we have a force diagram. I've got my zigzag force at A, which I'm going to eliminate by taking moments. So if I take moments about A, then that makes the problem easy to solve, because I need to know the horizontal distance from A to the 5G in order to get the moment for 5G. So we've got 5G clockwise times 2 cos 30, and that's going to balance the counterclockwise moment, which is 3 times T. Well, that's very easy to get T, isn't it? So T is equal to 10G cos 30 over 3. 10G cos 30 over 3. There we are, and the calculator gives us some numbers, taking G as 9.8, 28.29, so our final stroke is to express the answer that was requested to an appropriate degree of accuracy. Well, that brings us to the end of this presentation. The next one will be the study of ladder problems using the same principles.